To create signals, we want to use the existing operations in our sequence editor. For this, we need to go to the electrical section, create signals from our operations, and then choose the ones we need and rename them. We always need a symbol table in which the signals are defined, so we create a new one. To control our movements with our signals, we need to deactivate our sequences in our sequence editor. We find or define signals in the physics navigator. Signals can also be defined without sequences. For this, we select the signal option in the electrical section. Out of the MCD perspective, a sensor signal from our simulation is an output, and a control signal from other programs for an actor, for example, is an input. We can also define different data types according to our application. By data types excluding booleans, we can also define the unit. We don't use that option because there is a bug. Also, we can define an initial value. In the end, we add our signal to the existing symbol table. In order to connect signals to the model parameters, we use runtime expressions. This is also a workaround for a bug. We can select our objects and our parameter which we want to manipulate. Then we select a signal or another variable to influence our parameter. In the end, we can define a formula processing or influencing variables. In this case, we just need our signal value. In order to export and import signals, we can go to the Signals tab of the electrical section. Export can be done in two possible formats. In the CSV format, the values are separated by commas. In the SIMAT format, values are separated through tabs. After we have created our export file, it can be viewed in the editor, for example. Here we can see that the values are separated by tabs. Because of varying lengths, the columns are not clearly structured. In a similar manner, we can import signals, also from TIA-Portal, for example. In our case, we import a file with the same structure as the exported one. We add them to our symbol table. Afterwards, we can see them in our physics navigator. There we can also modify them if needed. We still need to connect the output signals with the sensors and the controls. If the input is a boolean, we can connect them directly with our parameter. If it is not, we need our workaround over runtime expressions. So in our runtime inspector, over right-click, we create a new runtime expression. For this, we choose our model parameter, the influencing signal, and a formula to calculate the desired effects. An alternative way to create runtime expressions is over the mechanical section under Custom Behavior. Now we deal with binary output signals for specific positions. To make our work easier, we create a reusable expression block template. First, we decide for a name and have the option to provide a description. Second, we define input parameters we want to use without connecting them to an actual object. Here we define speed and position. We also have to pay attention to the data types and the measure type. For speed, we need velocity. For position, we need length. Third, we define our outputs, which are true-false conditions, so booleans. Fourth, we create parameters, which will help us to calculate our desired effect. In our case, we want to specify a tolerance for a targeted position. We have to define our tolerance as unitless because it shall be used for speed and position. For simplicity, we don't use states here, so fifth, we set our expression by defining a formula how our output signal shall be set through processing inputs and parameters. Next, we actually use our expression block template, selecting expression block in the mechanical section. Here we select our template we created and modify it according to our application. We replace symbolized names like speed through a concrete model parameter by selecting it in our overview. We do the same for our outputs by selecting the right signal. Don't forget to confirm the changes by clicking the check mark. Our parameters we adapt through defining concrete values. In our expression, we already have the formula for our output defined, so we can give the expression a convenient name and confirm by clicking OK. To demonstrate the function of our expression blocks, we will manually change values of input signals in the Runtime Inspector and watch what happens to our output signal. As soon as the elevator arrives at its end position, the value is true. The mapping is now complete for one output signal. In order to repeat these steps for all other signals more easily, we rename our controls according to our signals. After the renaming, we can use our expression block template to match our output signals with specified position and speed conditions. We use these values for that. There is one output signal left to be created. This one shall signalize to another program like TIA-Portal that our simulation has begun and we are ready to communicate. We connect a new runtime expression to the signal with a special kind of formula. We use the function SIM-elapsed time. If we are at the start of our simulation, so below 0.1 seconds, our signal shall be then true, else it shall be false. We set the time scaling down to 0.1, prepare our Runtime Inspector with our signal, and start the simulation to view our signal switching. On the left-hand side, we see all the signals we defined for our communication. Inputs need to be set through our communication partner. Outputs are there to provide the partner with information of the simulation states. Right now, our signals are not connected to any other program, so when we start the simulation, nothing happens. In TIA-Portal, we have inputs fitting to the outputs of MCD and outputs fitting to the input of MCD. We named those objects accordingly. This is good for clarity in programming, but automapping doesn't work with this naming. Automapping only works for signals that would be named both in MCD and TIA-Portal the same. Instead, we will map manually. Now we start PLCSIM Advanced. We double-click on the PLCSIM Advanced shortcut on the taskbar. Then we see a message appear. It informs us that we need to use a right-click on the tray icon to activate PLCSIM Advanced. In the pop-up window, we click on the drop-down icon to create a new instance and provide a name with minimum 3 characters. Then we press Start. Another message appears and informs us that a new IP address was found. This is our virtual PLC. As next step, we load our program into our virtual PLC. We connect ourselves with the PLC, compile the software, and load it into the PLC. There are different ways to achieve this. Here we have a prepared watch table. It can visualize the current states of our outputs and inputs. Right now we see the start values. It may occur that we need a factor 1000, like for our transport surface, to correctly transfer our information. This is a bug. Now we display MCD and TIA-Portal next to each other. We go to the section Automation and select the option External Signal Configuration out of the drop-down menu of the bottom right corner. MCD remembered an earlier connection, but does not know the current instance of PLCSIM. This is why we need to refresh the available instances. Now the signals from TIA are known to the MCD. We select the signals to be forwarded. In our case, we select all. Afterwards, we need to map the signals. We do this over the signal mapping option. Here we choose which TIA signal should be connected to which MCD signal. Auto mapping only works if the name is identical. In our case, this only applies to our variable SIMSTART. After this, we have to manually select all the matches. Possible connections with diverse direction and same data type, like Boolean, are highlighted blue. Don't forget to confirm the mapping through pressing the button in the middle. For simplicity, sort by name and then assign. We have to pay attention at our signal out 2-axis Y container 2 because we didn't use it on TIA's side. After our connections are done, we can view our movement and validate the functionality. We see that the movements are correct and the signals are set at the correct place and time. In order to connect with a real PLC over TCP/IP, we need to go to the tab Automation and then MCD Signal Server Configuration. On the tab TCP Signal Server, we define the binding address over which the PLC is reached. As port we can choose 6000, but this also depends on our PLC. We create a new connection. To do this, we assign a name and the IP address of the PLC. Because of a bug, we first need to click another field before we can edit the IP address. Having done that, we specify the data signals which should be sent over this connection. To simplify the selection, we sort by name. Let's take a quick look at the PLC program. There, data blocks for sending and receiving data were created. The PLC program builds on the sample project for TCP connections from Siemens. Now we adjust the offsets. In TIA, this already happened. We still need to do it in MCD. Note, the input of MCD is the output of the PLC, so the offsets of receiving data MCD and sent data TIA need to equal. A double needs 4 bytes. Therefore, we have an offset distance of 4. A Boolean needs 1 bit. Nevertheless, a distance of 1 is not possible because of the TIA data block with a structure of reals. We do the same procedure for the data to be sent from the MCD. Here we only have Booleans in both structures, so we can use an offset of 1 bit. We have to pay attention at our signal out 2-axis Y container 2 because we didn't use it on TIA's side. Therefore, we deselect the signal. Also, our buffer has to be sufficient, but MCD warns us if this is not the case. Careful! Don't just click OK, but put MCD server into listen mode. Otherwise, no connection can be established. Also, when the project is reopened later, the server first must be set to listen mode. At this point, we would like to give a rough outline of the main program on the PLC with tsendc and trreceive. In our first network, we sent the data with tsendc. The parameter REQ responds to a positive edge, so it must be set to 0 periodically, which happens here by a negated done send. In network 5, we receive the data with trcv. The data is stored in RCV data, which is at the input data. Here's what we do in network 6. For data consistency in one cycle, we temporarily switch off our data receive function through a second function call. In network 7, we call the actual program logic. We hand over our received data and receive the processed sent data. All other networks are of minor importance. After we started our program on the PLC, and since our server on MCD side already listened, we can now start the simulation and view our known behavior. Before this video ends, let me also show you a quick little hint on our data blocks. We have to deactivate the optimized function. Otherwise, you won't be able to see the offsets here and here. You click Data Blocks, Properties, Attributes. Last, we have a quick picture of the general data block that we used.